This is homework number 9, and we're going to talk about primes. So let me just, before we dive into any more of the problems, let me just talk about primes for a minute. What are primes? Primes are numbers that only have two numbers that divide into them. One and itself. Right, so that's what a prime is, first off. A number that can't break down anymore. So why don't we make a list of primes real quick? I'll start with 2. Right? 2 can't be broken down. The only things that go into 2 are 1 and 2. How about 3? Is 3 prime? 3 is prime. How about 4? Why is 4 not prime? Because 4 is 2 times 2, huh? 4 is made out of other stuff. Y'all with me? So 4 is not prime. How about 5? Is 5 prime? Good. How about 6? What goes into 6? 3 and 2. So again, a number is prime if we only have, I forgot my plural there, huh? Numbers that only have 2 numbers that divide into them, 1 and themselves. So like 5 is prime because the only things that go into 5 are 1 and 5, right? And 3 is prime because the only things that go evenly into 3 are 1 and 3, etc. Okay, so 6 is not prime because there's more than just 1 and 6 that go into 6. There's also 2 and 3. All right, keep moving. 7, is that prime? Yeah. Yep. Do I need to check any more even numbers? Is there any other even primes? Why not? How do you know that no more even numbers? Pick any even number you want. 26. Why is it for sure not prime? Because 2 goes in. Right? You're only prime if nothing else, other than 1 and yourself, of course, go in. Well, any other number that's even, 2 goes in, huh? So there's no other even primes. There's only 1 even prime. All right, so I'm only going to check odd numbers now. No use even thinking about even numbers. So how about 9? Is that prime? No, what goes in? 3. So 9's not prime. Let's keep going. I'm not even going to check 10. Just move to the next odd number, right? 11. Is 11 prime? Yeah, nothing else goes in, huh? 13. Is 13 prime? Yeah, nothing goes in. 15. Is 15 prime? What goes into 15? 3 and 5, right? Something other than 1 in itself. So 17. Is 17 prime? Nothing else goes in. Or you're starting to push the limits of your immediate knowledge. Feel free to grab a calculator. 19, because they start getting a little higher here. 19. Anything going to 19? Nothing. 21. 3 and 7. So that's not prime, right? 21 is made out of 3 times 7. By the way, let me halt the list for just a second. What do we call these numbers that are not... Well, there I am. I'm writing it. They're called composites. As I was asking the question, I was writing the answer. They are composites because they're composed out of other things. So that would be, all the non-primes. So that just means non-primes. They're not primes. They're not the basic building blocks. They're made out of other things. They're Johnny-come-latelys, right? They're not originals. They're just made out of other things. So that would be like the number 4. He's just made out of 2 times 2. 6, he's just made out of 2 times 3. 8, he's made out of 2 times 4, or 2, however you want to say it. 9, and on you go. There's an infinite number of them. They go on and on. Basically any number that's not prime. Okay. Technically 1 is not prime. I know we tend to think of it as prime. It's not prime and it's not composite. It's in neither category. It's all alone. 1 is the only lonely number. Sorry, I'm just doing this on there. All right, so 1 is the only one that's not in either category. And why? According to this definition right here, why would 1 not be in that category? How many things divide into 1? Just 1. How many do you need to be prime? 2. So technically prime means 2 things go in. 1 and yourself. you're not 1, right? So anyway, I'm not going to test you on this. It's kind of a dumb little thing, but I just want to let you know. 1 is not a prime technically. So the primes start at 2, and they go on up, and the composites are all the numbers composed, made out of other things. Let's keep going. How far do the primes go? What's the next odd? 20, well, we did 21 already. It's not prime. 23. Is that prime? Yeah, nothing goes into it. 25. Is that prime? Nope. 5 and 5. 27. That prime? 3 times 9. 3 times 9. Yeah, feel free to use your calculator if you're rusty on some of these old times tables. 29. And nothing goes into 29. You can try stuff on your calculator. Well, I'm supposed to leave it there, huh? 29 is prime. All right. 31. Is 31 prime? Nothing goes in. You can try it in the calculator. Nothing goes in. 33. So it is prime. 33. No, what goes in? 3 and 11. Yeah, 3 and 11. Next odd number. 35. Anything that ends with a 5. 5 goes in, huh? Right? 5 times 7. No way. 37. Yeah, nothing goes in. You can try to calculate. 39. There's a little trick for 3. If you add up the digits, 9 plus 3 is 12. If 3 goes into 12, 3 goes into 39. It's a little trick. You use your calculator, though. You don't need to just try it. 3 times 13. 39 is 3 times 13. So it's not prime. And they keep going forever. I'm tired at this point. All right, so they keep going forever. So now, what they're going to do is they're going to ask me, well, let's just get back to it and we'll see. So there's a bunch of the primes. They go forever. The composites are the non-primes. 1 is neither category. Okay, so with that in mind, let's go back and answer some questions. We did 1 and 2. We're on 3. So they're asking us 1664. Let's jump on to number 4. Let's jump on to number 4. Is saying is 103 prime. That'll make more sense. We'll go back to number 3. Number 4 says, is 103 prime? Is 103 a prime number or not? There'll be one of these on the test. This is on the practice exam. I made a practice exam to help you know exactly what would be on that test. There will be no surprises. So anyway, you'll see this on the practice exam and on the real exam. So how do you take a big old whop? You get your calculator. You have your calculators during the test. So how do you take your calculator and figure out if a big old number like that is prime or not? Well, you got to start dividing by other things, huh? Now, think with me. Think with me about this. Let's think our way through this. I want to arrive at a way to do this easily because, let's start off. So basically, if we're wondering this prime, the question is, does another number divide in? That's really what we're wondering, right? Is there some other number that goes in? And, of course, you got your calculator in the test. You can just whip through, but you don't really want to try all the numbers from 2 to 102. That would use up your whole test time. You wouldn't get anything else done. And it's just one question. So we need to see if we can make some logical observations to make this quick and snappy. So let's start with 2. Does 2 go into 100? You know it doesn't because that's not even, huh? 2 only goes into numbers that end even. So no, 2 doesn't go in. Does 3 go in? Try it in your calculator. There's the trick for 3. 1 plus 0 plus 3 is 4. Does 3 go into 4 evenly? No. So it doesn't go into 103 either. But you can just try it in your calculator. Just take 103 divided by 3. You'll get some decimal thing. It doesn't go in evenly. Keep going. How about 4? Does 103 divide by 4 evenly? No. And why could it not? Why don't I even need to check 4, really? If 2 doesn't, we've already said 2 doesn't go in there. Could 4? What's 4 made out of? 2 2s. And now you want to best primes. Thinking about primes, especially in the next section, stuff we do next week, you'll see the power of primes. If you think about primes, you can answer hard questions that easy. If you think about what they're made out of. So always be thinking about what are these numbers made out of. So when you look at 4, you want to think 2 2. I already know 2 doesn't go in, so no way 4 goes in. How could 4 fit in there if 2 doesn't, and he's got 2 2s in it? No way. So I don't even need to check 4, do you realize? So I'm not even going to put 4 in the list. I don't even need to check 4. I already know 2 doesn't go in. Let's go to the next number, 5. Does 5 go in to 103 evenly? No, it doesn't end with a 5 or 0. You can try it in your calculator. 103 divided by 5, no way. You're right, it's got to end with a 5 or a 0 for 5 to go in. You know, like 15 or 20 or something like that. So no. How about 6? What do you think about 6? 6 is not a prime. He's made out of other numbers. So when you see him, you should think about what and what? 2 and 3. 3 and 2, either order doesn't matter, right? When you see 6, you think 2, 3, 2, 3, 2, 3. Do you think 2, 3 goes in? But we already know neither 2 nor 3 goes in. We don't need to check 6. He's just made out of 2 and 3. We already checked 2 and 3. You're starting to see the power of thinking about primes? We don't even need to check 6. Let's go to the next number, 7. I don't know. Try it on your calculator. Honestly, I have no idea. 103 divided by 7? Tell me. What is it? Some 8, 9, 10, 4, I'm not even close. 14.7, blah, 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 whatever. So it's no. It doesn't go in evenly. Let's go to the next number. 8. What do you think about 8? Yeah, he's made out of 2 and 4. He's not a prime. He's made out of other numbers. 7 was a prime, so I had to check 7. 7 wasn't made out of other things. He's a building block. He's a prime building block. But 8, he's made out of 2 and 4. I already know 2 doesn't go in. Hold on. Can we make a logical observation at this time? Do we need to check any more composite numbers? No. Do you realize if you check the primes, you've checked all the numbers because the other ones are just made out of the primes? You getting the logic there? The only numbers that matter are primes. I don't know if you've ever thought about numbers that way. They are far more important numbers because they make all the other ones, right? So if you just check all the primes, you will have checked all the numbers because the other ones are just made out of the primes. You tracking with me? So that's our first and huge logical observation. Let me write it somewhere. Only check primes because the other numbers, the composites, are just made out of primes, right? So if you check all the primes, you've checked all the numbers. The other ones are just constructed out of the primes. So that's observation. We're going to make 2 huge observations that'll make this way faster. So there's observation number 1. Don't waste your time with composites. So you got this list. You can totally you get a 3x5 card on the exam. Put anything you want, any kind of notes you want, front and back of a 3x5 card for our exam week after next. I would put that list of primes right on your card. You just go down the list. Right, where are we at? 2, 3, 5, 7. What comes next? 11. Just go to the next prime. So let's try 11. Just take it, and you have your calculator with you. 103 divided by 11. I'm thinking no. What is it? What is it? 9.3. Whatever. Blah blah blah. No way. Next prime number on the list after 11. 13. Try 13 on your calculator. What is it? Well, wait. Hold on a minute. Did you know we're actually done? Why? That's the other logical observation. Basically, how do I say this in a way that makes sense for you? Let me write the rule, and then I'll give you a reason for the rule. This is rule number 2. Here, let me come down here, use the same color. So there's rule number 1 up here, only check primes, right? Rule number 2, stop at the square root of the number. Stop at the square root of 9. I know that probably says, like, where'd that come from? I'll give you a reason in a minute. What do I mean the square root of the number? If you take our original number, our 103, and you square root it, what's that? You guys have your calculator? You know the square root button? It's 10 point something. Yeah, square root of 103. You know how to find that in your calculator and everything? Going to use the calculator in the exam, right? Square root of 103 is 10 point something. That means as soon as you have gone up to 10, on the primes, you don't need to check anymore. In fact, I was really done back here. The next prime was 11. I didn't even need to check 11 because it's past 10. You can stop at the square root of your number. Stop checking primes at the square root of the number. So all you got to check is 2, 3, 5, and 7, really. None of those go in. Done. This is for sure, with 100% confidence, a prime number. Now, I haven't given you a reason for that second logical observation yet. But it's true, and I'll show you. So everybody see the process first up before I give you the reason why it works. So all you got to do is, if you want to know if this, so I'll give you a big old whopping number on the test. You see it on the practice. I'm like 2,519 or something. And you don't want to just go based on looks, because they might look prime but not really be prime. And so the way you're going to know is you're going to take the square root of the number, and whatever you get there, that's how far you have to go in the prime list. And then you go back and go, okay, and just go down the prime list with your calculator, one at a time, till you get to that spot. If none of them go in, then it's prime. If somebody goes in, then it's not prime. All right, so why? So let me give you the reason why. Well, maybe we better do it one more time. Let's try a big one. I'm just going to make one up. 257. Honestly, I have no idea. I just made that off the top of my head. Is it prime? It sort of looks prime to me. But again, don't go by looks. There might be some weird number like 13 or something that goes in. I have no idea. So how should you do this process? Let's first off take the square root of the number, right? So you know how far we need to go on the prime list. Y'all have your calculator? What's the square root of 257? You want it? Cell phones are fine today, but remember on test day in 2 weeks, you won't be able to use a cell phone, of course. So make sure there's some calculator you're comfortable with using. You don't want to, like an athlete show up at the ball game with a brand new pair of cleats on game day. You don't want to show up with a brand new calculator you've never used before on test day. Make sure it's something you're comfortable with. Square root of 257, what is that one?
I got 16 points.
16 point, whatever, blah, blah, blah. Great. That's good enough. Okay, so that's where we stop. That's our stopping point. That one's not actually a prime. We stop at whatever prime's right before that. So let's go through the prime list. You'll have that on your 3x5 card here. 2, 3, 5, 7, blah, blah, blah. So 2, 3, 5, 7, 11, 13. And that's as far as we need to go. The next one's 17. I don't need to go there because that's over my 16, the square root of the number. Making sense? So I just need to check these primes, and if none of them go in, then I know for sure that number's prime. So here we go. 257 divided by 2. You can just try your calculator. Nope. And then 257 divided by 3. That's a no. I can do that one by the shortcut rule. 2 plus 5 plus 7 is 14. 3 doesn't go evenly into 14. 3 doesn't go into 257. 257 divided by 5. No, it doesn't end with 5 or 0, but you can use your calculator if you're rusty on some of those rules. 257. Now that's the one I'm not sure of. Does it? Does 257 go? Does 7 go in? It doesn't. What does it come out to be? 36 point. Blah blah whatever. Okay, so it doesn't work. 11 also. I'm not sure about 11. No. So I'll just say no. And last one, 257 divided by 13. That one's a no as well. Okay. So then that number is a prime. That number is a prime. Is that making sense? Is that little process there making good sense? How about, let me see if I can, I'm going to try to make one up really quick here. Okay, I got one. So here we go. I want you all to try real quick. 221, is it prime? So try that one. 221, is it prime? $221 is a prime. So start with the square root thing. Find out how far you need to go. And then start going down the prime list. Does it look prime? It certainly looks prime, doesn't it? But again, we don't want to go by looks. There might be something good to it. That's true. So square root of 221, what is it? 15, 14? 14 point whatever. So then the primes you need to check. Use your calculator. 2, 3, 5, 7, 11, 13 will be the last one we need to check. Because the next one will be 17, don't need to go there. So you take 221, divide by 2, no way. 221, divide by 3, no way. I can tell by the shortcut rule. 2 plus 2 is 4, and 1 is 5. 5 is not divisible by 3, so neither is 221. 221 divisible by 5, no way. It doesn't end in a 5 or 0. It's the only way it can work for 5. 221 divided by 7, I don't know. I'm thinking it's no. Right? And then 221 divided by 11, I'm thinking it's no again. And 221 divided, last one, divided by 13?
No.
13 and 17. Not prime. Even though it had the prime look. 221, is it prime? No. 221 breaks down to be 13 times 17. He's just a composite. He's just composed out of 13 times 17. He's not a prime. Is that making sense? Feel like you'll be able to do that? Good. Questions on that? Now, why the square root thing? Why is that true? Let me give you a reason for that. Because I don't like giving math without reasons like it's a magic trick. It's not. There's reasons for everything. Because that was a huge help to us, right? You understood the reason why we only need to check primes. Because the other numbers are just made out of primes. So, right, if I've checked all these primes, then I've checked all the numbers they can make. So, but why the square root thing? Well, if you think about what divides into, we're checking for what goes into a number. If you think about, let's take 100, nice clean number you all know about real well. If you think about, like, does 2 go into 100? Now, lots of things, it's not prime, I know, we all know it's not prime. But let's just think about how the multiplication, the dividing in works. 2 goes into 100, right? If I tried to divide, well, let me just write it the way we were dividing it. Write 100 divided, that's how we're writing it, right? Yeah. Take 100 and divide by 2. What do you get? Well, you get 50. Okay, great. So now, go up the line. 3, it doesn't go into 3. Take 100 and divide by 4, you get 25. Just watch this pattern with me. Math is patterns. It's just totally patterns. 20. 100 divided by 6 and 7 and 8 and 9 those are all no. And then 100 divided by 10 is 10. Take a look at a pattern with me. To see what's happening. Well, let's do one more. I'm jumping the gun on the pattern. I'm gonna skip 11 through 19 are all no. And then if I come down here and divide by 20, I get 5. Okay, now let's look at the pattern. Look at the numbers. I'm just showing you what happens when you try dividing a number. That's what we're doing with the prime thing. We're trying to divide different numbers, seeing what goes in, right? Well, look at this logically with me. See how these numbers are going what? Up or down? They're going up. And what are these numbers over here doing? Going down. That's because you're taking two things that multiply to be 100. So if the number on the left is bigger, the number on the right's got to be smaller, right? Let me write a few and make sure this is all good sense. Right? You see what I'm saying? Basically, when you're trying to divide by a number and see if it goes in, you're trying to find two numbers that make your 100. When you're saying, does 2 go into 100? Yeah, 50 times. That means 2 times 50 is 100. So as you're going up the line in the numbers you're trying to divide by, up the line, if it does go in, the number it'll multiply by is coming down, 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 right? Like if 5 goes in, it's got to go in less times than 2 went. Was that too quick? Right? 2 goes into 100 a whole bunch more times than 5 does. If I had a group of 100 people, and I said, break into teams of 2. Well, there's 50 teams of 2. I said, okay, now you group of 100 people, break into teams of 5. Well, there's going to be less teams of 5, right? 5 goes in less. So the bigger the number you're trying to go in, the lesser. So these go up, and these come down. Okay, so what? Well, my point is, and what's the square root of 100? 10. Notice, as soon as we go beyond 10, look at this, 2, 4, 5, 10. Once I go to 20, that's the first one bigger than the square root. He goes in with a number smaller than himself. Do you see that? Look at this. The number on the right's bigger. The number on the right's still bigger. The number on the right's still bigger, but they're getting closer, aren't they? Now the number on the right and left are the same. Now the number on the left is the bigger one. What just happened? We passed the square root point. See, the square root is the number times its very self. That's what square root means, right? You know the square root of 100 is 10 because 10 times its very self is 100. So once you go beyond the square root point, any number bigger than the square root is going to have to multiply by a number smaller than itself. And you think, okay, so what? Well, we've already checked the number smaller. Back here. I don't need to keep going. You see, once you go by the square root point, if something like 20 or 50 goes into 100, which they both do, as you know, 20 and 50 go into 100, they'll have to go in with numbers smaller than them. Right? 50 goes in times 2, and 20 times 5. And you've already checked the numbers smaller than them back here. So you don't need to go beyond the square root point. That's why the square root rule works. Once you get there, anything after that is smaller numbers. The secondary numbers are smaller. And you've already checked them. So it couldn't be, right? If I'm trying 20 and it's going in with a smaller number, I've already checked. If none of those smaller numbers went in, how could the bigger numbers? Like going back to the 221, for example. Think, well, maybe I should check 221. Well, of course, that one turned out to be prime. 257. Yeah, what if I said, well, 257, you said stop at 16, but maybe I should try 17. No. Somebody have a calculator. What is 257 divided by 17? Somebody have that for me? It's a tough, crazy decimal, but what do you got? 15 point blah, 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 blah. Okay. Blah, blah. You see, if 17 really did go in, it'd have to be something like 17 times 15. I know it's not exactly 15, but it'd have to be something like 17 times 15. Well, so what? I've already checked the numbers up to 15. I know it can't be 15. I already checked those smaller numbers. So 15 can't go in. So 17 can't go in. Because it would have to go in with 15 and I already checked 15. 15's not prime, but I checked up to that point already. Is that making sense on that? So anytime you go past the square root mark, it would have to multiply by a number smaller, and you already checked the number smaller. You know they don't go in, so this bigger thing couldn't either. So that's how we check the prime thing. 3. For number 3, they're saying, what's the greatest prime you must consider for 16? See, now we know 1664 is not prime. Obviously, 2 goes into it. But they're just saying, suppose you didn't know that, how far would you need to check? Well, take square root, right? Square root, 1664. Somebody have that? 40.79. 40.79, blah, 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 blah. So what's the biggest prime that's just below 40? Let's go back to our prime list. I don't remember. Whoop, there it is. No, that's not our main prime list. There it is. 37. 37 is the biggest prime. The next prime after that would be 41. So the biggest prime just under 40 is 37. So you want to have that prime list on your 3x5 card. Everybody see that? So 37 is the highest prime you would need to check. That's the last prime under 40. So the answer to that question is 37. That's the greatest prime you would need to check. We good? Should we go on to number 5? Okay, number 5. Find the least natural number that is divisible by 3 different primes. So now, they're saying you want a number. Natural number just means like regular number, not a decimal, whole number. That is divisible by, like they can go into it, 3 different primes. Think about what they're asking. They're saying, can you find the smallest, they're basically saying smallest number that 3 different primes go into, divide into. So how are we going to figure that out? What a weird question. That's a great thought. That's exactly it. Just take, what are the 3 smallest primes? 2, 3, and 5. If you multiply those together, what is that? 2 times 5 is 10, times 3. That's the easy way to multiply. Just let them make the 10 first. In order, right? It's always going to be the same. 10 times 3, 30. I usually go 6 times 5, 30. Whatever, it doesn't matter. 30. 30, that is a number that is divisible by 3 different primes. 3 different primes go into it. These 3. 2 goes into 30 evenly. 3 goes into 30 evenly. 5 goes into 30 evenly. Right? 5 times 6. 3 times... Yeah, right? And that's the... How do you know that's the smallest one? How do you know there's not a smaller number? Well, because that's made out of the 3 smallest primes. There couldn't be a smaller number that 3 primes go into because we used the 3 smallest primes to build it. Make sense? See the power of primes? If you were just trying to guess around in numbers, it'd take forever. But if you think about primes, you go 2, 3, 5. Let's multiply them together. All right. Good observation. Let's try, I think we did 6 before. Here, I'll go to fresh screen. We did one like 6 anyway. We can do one more. Let's take that number. They're asking, find the prime factorization of that number. Can you do that really quick? Or really slow? Either way. Can you do that? Can you take that and find the prime? Break that thing down to primes. Here, let me make it a little bigger. It's 33 to the 5th times 39 times 49 to the 14th. So some of those numbers are not broken down. Well, none of those numbers are broken down. 33 breaks down, use your calculator. 39 breaks down. 49 breaks down. Use your calculator if you're rusty on some of those. Some of those are bigger numbers. And find out what goes in there. And then answer the multiple choice thing there. So 33, 3 times 11, 39, 3 times 13, 49, 7 times 7, to the 5th, and this one's to the 14th. Good so far? So I just broke down the 33. 33 is 3 times 11, 39 is 3 times 13, 49 is 7 times 7. And now what? What is this 5 power that was on the 33 is now on both the 3 and the 11? What does that mean? Well, you don't write this out, but you all know. I just want to be sure we all do know. I'm sure we do. It means 5 of those, doesn't it? Don't write this out. This is not the good way to do it. I'm going to erase this in a second. But let's all be clear in your minds. It means 5 of those. That's what those little numbers in the upper right-hand corners mean, huh? They're repeat symbols, aren't they? It means 5 of those. But that's not a very nice or efficient or easy way to write it. But make sure you know that in your mind. That is the meaning. So what's the shortcut way I could do that? I could just say 3 to the 5th and 11 to the 5th, couldn't I? Because you could rearrange all those. It means 5 3s, 5 11s, and then there's the 3 here and the 13 there. And then now, how many 7s we got all together? 28. Why? There's 2 7s 14 times. Aren't there? Right? Doesn't that mean 7 7, 7 7, 7 7, 7 7, 7 14 times? You tracking with me? Now, if you want the formal, well, yeah, let me not give the formal. Just looking at that for a minute. You see what I'm saying there? That's 2 7s. That's a pair of 7s 14 times. Just 7 7, 7 7. You know, 14 of those. So 14 groups of 2 is 28 7s, isn't it? The formal rule from your algebra days is, it could be done as well. It's not required. But if you want to just say, well, can't we just make that 7 squared, Mr. Aaron? Yeah, absolutely. And then 2 times 14 is 28. That's right, too. Whatever gets you to the 28 is great by me. I never care how you get there. As long as you get the idea that it's 28 7s, right? Now, what else do we have to do? Is this our answer? Not quite. One more step. One tiny step. This guy and this guy need to be lumped together, don't they? How many 3s do we have all together? Yeah, 1 more here, 5 there. 6 3s, 11 5s. I guess I should put them in order. Whatever, it doesn't matter. 7 to the 28, 13. So whichever one has that answer. 3 to the 6, 7 to the 28. A and C. I'm confused. Is it D? A's close. What's wrong with A? Oh, it doesn't have the 5th power on the 11. Yeah. All right, yeah, so it looks like it's D. We good with that? Did you track with what I did there? So I just took that 33, 3 times 11 to the 5th. So it's 5 3s, 5 11s. 3 and 13. And 49, 2 7s, 14 times, that's 28 7s. Then I just put these together, 5 3s and 1 more 3 is 6 3s. And you can put them in any order, it doesn't matter. All good? Okay. Is 7 to the 3rd, 7 to the 3rd times 11 to the 5th, that whole thing there, is it a factor of that? Now, factor means divides in evenly. Feel free to write this stuff in your 3x5 card if it helps you to get the terminology down. Those are synonyms. Right? That's like saying fast and quick. They mean the same thing. So, factor of or divides into, same thing. Totally synonyms. So when they say, is this number here, the whole thing, the 7 to the 3rd, 11 to the 5th, is that a factor of this number? They're saying, does 7 to the 3rd, 11 to the 5th, does that divide into 7 to the 4th, 11 to the 5th? Meaning, is it a part of it? Is it a container? Is it already in there? Yeah. Yes, it is. Yes. Yes, it is. I'm not going to do all those too weird, I'm just going to say yes or no on the test. I'm not going to do all those special reasons. It is because basically if you take 7 to the third times 11 to the fifth, you would just need to multiply it by one more 7, and then it would become the other number, huh? That's what they're saying here, times another 7. Anyway, don't worry about that stuff. I'm not going to quiz you on that. Just yes or no. Does everybody see that? So dividing in, being a factor of, means you're in there. Your container is this already contained in there. Yes. Now, what if we had, let me show you what would not work. What if we had like another 3 out here? Then we say, no, he's got stuff that's not in there. That's not a factor now, not a divisor. So it just means, are you in there? It's as simple as that. When you're looking at primes, you just say, is it in there? All right. Mr. Arborita. They're doing the tree name there, right? Arbor Day. Mr. Arborita wants to plant fruit trees in a rectangular array for each of the following number of trees. Find all possible numbers of rows. And if each row is to have the same number of trees. What are they talking about? Let's do part B. That'll be easiest. We'll start with B, 28. So I'm going to come over here. I'm just going to make it clean. Basically, the Mr. Arborita problem. What it's saying is he wants to make a rectangle of trees, and they're basically saying how many ways? How many different ways are there for him to make a rectangle of trees? I'm going to do part B, where he has 28, right? Yeah, 28. If Mr. Arborita has 28 trees, he's going to plant them in a big rectangle. So what are all the different ways he could do that? He could do 7 trees, 3, 4, 5, 6, 7 trees across. You know what I'm doing, right? 7 by 4. 7 and then there we go. He could do a big 7 by 4 rectangle, couldn't he? That's one thing he could do. I don't want to I'm not going to write any more dots, but he could do other things too. We're going to try to figure out all the different things he could do. So everybody getting the general idea first off. They're saying, what can Mr. Arborita do? He could plant 4 rows of 7, right? That's one thing he could do. Let me get rid of this. But there's other things, huh? Basically, they're asking, what are all the different, right? He could go, for 28, he could plant 4 rows of 7. What else could he do? Do what's that? Yeah, he could do 2 rows of 14. Right? 14 trees, 14 trees. That'd make a rectangle. What else could Mr. Arborita do? 1 big row of 28. I know that might not seem like a rectangle, but it is. It's kind of more like a line. And you think, that's a line. Yeah, but, does it include the 1? Yeah, we're going to include the 1 as part of the answer there. Here, let me know. Even include the 1, even though it might seem like a line more than a rectangle. We're including. What else? Is there anything else? Is there any other way Mr. Arborita could plant the trees? I don't think so. I think that's it. Let me write them out. So basically, he wants to know. They're asking for, what did they say? Find all possible numbers of rows. So how many different you could have? So possible number of rows. What are the you could have? 1. So just what are all the numbers here? 1, 2, 4, 7, 14, and 28. That's the answer. Those are the different. He can have rows of length 1, 2, 4, 7, 14, or 8, or 28. If he's going to make a rectangular array out of his 28 fruit trees, he can have rows of those amounts. Does that make sense? Now, what we really want is a method to do this that's more systematic. That was just a little bit haphazard because it gets harder. Let me show you what I mean. Let me go back to question A. It's 196, yeah. So has everybody got that one down? Well, I'll just write it right on here. Let's back up now to question A. And that one says 196 trees. 196 trees. At this point, we need a game plan that's reliable. We need like a system, like step 1, step 2, step 3, because it's just going to be too hard to just kind of randomly grab numbers that multiply. You might miss some, you might be sure you get them all. So here's the game plan. Here's what you do. So with these last 6 minutes, I'll show you to find, and what we're finding really is all possible factors, divisors, whatever you want to call them. Divisors, right? Numbers, yeah, you know what divisors are. Numbers that divide in, right? That's really what they're asking us, huh? They're saying, look, take 28, what are all the numbers that go into it? That's really that whole Mr. Arborita, da-da-da-da-da. They're just trying to make it seem creative. But bottom line, they're saying, what are all the numbers that divide into 28? There they are. Those are all the numbers that divide evenly into 28, aren't they? So how do you find all the numbers that divide evenly into, like, especially when they give you something whopping big, like 196. You don't want to spend forever on your calculator. So we need a game plan at this point that's quick, reliable. So let me show you how it works. Here's what you do. Let me just do it for the 196. And then, well, here. Step 1. Factor your number down to primes. Factor your number down to primes. And then make a table like this. And on the table, start with 1, and put a, let's call this prime A. This is A to the first, A squared, A cubed, dot, dot, dot. And this will be, I should probably make that nicer. And this should be B to the first, B squared, B cubed, dot, dot, dot. And in here, all divisors in the table. That's how it'll work. So that's the game plan. I'll show you how to execute it, and then we'll be out of time. We'll just do it on this one problem, and we'll be done. So to find all possible divisors, you basically factor down the number of primes. You make a table. Start with 1 and 1 in the upper corners, and then you just go take one of the prime, multiply, another one down, and fill out the table, and you got it. Let me show you. So let's do the 28. Let's go back. Let me factor the 28. We already know the answer, I know, but let's do this method where we already know the answer. So if you break down 28, it's 4 times 7, right? Now that's not all the way to primes yet. Why not? Why is that not all the way to primes? 2 times 2. Now it's all the way to primes, huh? So what's 28? It's 2 squared times 7. You tracking with me? That's the prime factorization, it's called. Prime factorization of 28. 28, that's the guts of a 28. It's made out of 2 squared times 7. Those are the building blocks of a 28. Now you go to your table and you say, okay, make my table. Start with a 1 here and a 1 here. Do my rows and columns. And then what do you do next? You take one of the primes, like on this side, let's take the prime 2 squared, this one. And then up here I'll do the prime 7 to the first power, which is 1, 7. So I take the 2 primes, the 2 squared and the 7. It doesn't matter which way you put them, it's interchangeable. Let's put one of them on top, one of them on the side, and then you just go 2 to the first, just 2. 2 to the second. We stop there because that's what it is. It's 2 to the second. And across the top, you go 7 to the first, 7 to the second. Oh, we don't have 7 to the second, so we stop at 7 to the first. So that's our simple table. They're going to get bigger on Monday. And then, is everybody seeing what I'm doing here first off? So I started with 1 and 1 in the upper corner, and then I just took one of the prime, you just put 2 to the first, 2 to the second, until you get up to your prime. And then on the other one, 7 to the first, 7 to the first is it. and then you just multiply these together, column and row. What do I mean? Take 1, it's a big multiplication table. 1 times 1, boom. 1 times 7, boom. So I'm just going to multiply. So 1 times 1 is 1. 1 times 7 is 7. 2 times 1 is 2. 2 times 7 is 14. And what is 2 squared? That's 4. 4 times 1 is 4. 4 times 7 is 28. See, there's the answers we already had. And I know this seems like, that was a lot of work. The other way was easier. I know, on a super easy problem like this, it's like we just took a fancy, amazing power tool to just put a little thumbtack on the wall. Yeah, it's overkill. That's way too big a tool for that job. But for the 196, it'll handle it nicely, and that's which we'll do on Monday. Does that make sense generally what I did there? That's the method that'll work for when they're ugly. So